These are the notes from the Atomic Spectra lab where we had spectroscopes that we looked through, and we had a tube, a glass tube filled with hydrogen gas, helium gas, mercury gas, we didn't do lithium, and neon gas. And when we looked through the diffraction grating, which is a part of the spectroscope, we could see that every element had these different lines, and they glowed different colors overall. Like mercury glows this like alien blue color, but when you look through the diffraction grating, you don't see that. So what the heck's going on? Because every single element has its own set of bands, and that's why this is called the element's fingerprint, the atomic spectra. Alright, little background information. The diffraction grating that was in the part of the spectroscope that was where you put your eye, these slits actually split light into, or these gratings split light into their various wavelengths and colors. Just like a prism splits white light into its rainbow, that's exactly what the diffraction grating does as well. The spectroscopes that we're using contain that diffraction grating. They also have a little scale bar, and this is so that you can measure the wavelengths of visible light. So you can see at around 420 nanometers, maybe, that's where violet light is, and then the longer wavelength, getting closer to 700 nanometers, that's the red wavelength. Some important terms you need to review to understand everything. Ground state electrons are the lowest energy state of an electron, and an excited state electron is when they jump up to a higher shell and have a higher energy. Temporary. It's very temporary, because what goes up must come down. So in class I have people jump up onto a table, like all the way up, and then when they fall down they throw a purple sheet of paper representing that they're releasing that purple photon, and then I have people jump up onto like textbooks and then jump back down, and they throw a red piece of paper down. So that's just a little human version of what's going on in the electron world. So again, when an electron absorbs energy, it will jump, and this could be energy from a flame or electrical energy, and when it ends up in the higher shell, that's unstable. So after it goes up, it actually moves back down, and in that process that's where it releases the photon of light. So the energy that's released is the difference between energy shell number 2 and energy shell number 1. And since every element is unique, based on those photons that are being released, we can tell what element we're looking at. So this set of bands or lines is actually referred to as an atomic emission spectrum. And that's what we see again when we're looking through that diffraction grating in the spectroscope. It produces this series of discrete spectral lines that are characteristic of the element. For example, here is helium's set of spectrum lines. Every single line corresponds to one exact frequency of light that's emitted by the atom. So you can use this, like I was saying, to identify unknown elements. That's actually how they understand which elements are present in the stars. And for example, the sun, that's how they came to understand that the sun is really fusing hydrogen atoms into helium, because when they looked through a diffraction grating at the sun, they could see helium's bands as well as hydrogen's. So in this little problem right here, I've got lithium's spectrum, hydrogen's, helium's, and sodium's, and you're supposed to figure out which ones must be present in this unknown. And I could see right here, based on these two lines, that there must be some hydrogen. And then I noticed that these two match up, so there must be some helium too. Yep, and sodium's band is not present, so sodium can't be there, and neither is lithium's. So this unknown is probably what the sun looks like because it's a mixture of hydrogen and helium. When you're looking at your spectrum, for example, you'll notice that hydrogen atoms emit this pinkish color. When the visible portion of the light is passed through the prism and it's separated into the different spectral lines, you don't see that pinkish glow anymore. You see a red band, a lime green band, a blue, a darker blue, and a violet. And I guess it looks lime green in this picture, but it's more of a teal in this one. Okay, so what's happening here? Well, because hydrogen atom has different spaces between its energy levels than other atoms do, and that's because it has one proton and one shell that has electrons. It still has all the other shells, but they don't normally have electrons in them. So you can see if an electron jumps from the first shell to the second shell and falls back down, that's actually a really big jump for it, and so it releases UV light, which we can't even see. Okay, and it gets complicated because when electrons can jump up and then they can jump up again and come back down, they can release red, the teal-y green color, the blue, the violet, etc. Okay, and they'll also release some, besides ultraviolet, they might release some in the infrared, which is the wavelengths are too long for us to see. So it gets complicated. But if you can understand this, then you're really understanding it as deep as I need you to. So how does hydrogen give off multiple bands of light? Because a lot of people think, what? There's one electron. How can it give off all these different colors? Well, we're not talking about one hydrogen atom that you're looking at in that gas tube. There are millions upon millions upon millions of hydrogen atoms, all which have one electron. So these electrons are jumping up to lots of different energy levels. And then they're falling back down and releasing these photons that are in the visible spectrum. And then specifically for hydrogen, we see these colors. Okay, and our spectrum in class, again, because of our limited ability, we really saw it as a red, a blue, and a teal, or a red, a teal, and a purple. We didn't necessarily see this darker blue. And you'll notice that I put them in rainbow order, and my example has it the opposite way. It doesn't really matter. So which bands are from the high energy jumps and which are from the low? The violet and the teal are from bigger jumps, and the red band is from a low energy jump, or many low energy jumps. Why do you think elements have different spectra? Did some sharing in class? Well, because every element has a different number of electrons and protons. This makes the energy levels unique, the possible jumps unique. Since the colors that are emitted are from these different jumps, every element emits its own unique set of colors. What if there were not quantized energy levels? So what this is saying is, how do we know electrons are at these specific distances? Well, if they weren't, we would see these jumps in every possible color. So when you looked through the spectroscope, you would just see all the colors. And in class, we did an unknown where we looked up at the fluorescent light bulbs, and we definitely saw some mercury in there because mercury is commonly used in fluorescent light bulbs, and so we could see the bands for mercury and some other bands as well. Identify the element. So this was helium based on your data that you took in class. This matches hydrogen. Okay, so you wouldn't know those unless you had been there for the lab. But that's it for the